a Fourier transform is not something that was designed to be done in a piece of electronic device, in an electronic device. It's very much analog effect. Let's just say it's a very analog effect. It's an integral. You have to solve the integral. The integral has infinite series, and you reconstruct the components that make up the signal itself. So what a Fourier analysis is you take a signal, for instance, that contains all of these signals added together, and when you deconstruct it using a Fourier analysis, you get the individual signals that go into it. So here we have a number of signals that, when added, they all make up, what your input signal is. So when you perform a Fourier analysis, you rip out, a 100 megahertz signal with a 1 megahertz, with 101 megahertz, oscillation on top of it. The Fourier analysis separates the two, and that's how we understand the frequencies and the information that's coming from a more complicated signal. It's not something that is easy to do on electronics, like I mentioned. So in order to do this, we usually use an FPGA or some kind of digital signal processor. And since digital signal processors are digital devices, they can't do math. They can't do calculus. So what we choose to do is, what we decide to do is to perform some kind of numerical approximation. So instead of an integral, we use a series. Instead of trying to solve for this line itself, we segment the line, and we just try to find individual solutions at each one of these peak points. Okay, so this is the notorious loss in quality that we notice, for instance, when we play a CD versus a vinyl music. Okay, so there's some of the deeper sounds are lost. Sure, you get a clarity, sure you get error corrections and things like that, but that's lost. What you would normally do if you had signals and all of these areas had information where you wanted to say this is 2.4 and that's 5 gigahertz, for instance, and you want to get information in there. Well, when you do a Fourier analysis, you grab the whole spectrum, window it, so you cut things out, and then you do a Fourier analysis over this area, for example, and try to throw away the garbage that you don't want. But with an ENL, each one of those frequencies is an ENL itself. So if you want 2.4 gigahertz, then you put a 2.4 gigahertz ENL in there, and you just get the information that you want. You don't have to collect all of this information and analyze it. That takes time. It's complicated. It produces aliasing effects, and it wastes time. It wastes time because you have to cut a certain piece of the signal, analyze it in the fast Fourier transform, then produce the output, then grab another one. So there's ways of people get around that by having multiple copies of the same information, so that one of them is analyzing. You have a parallel channel that's analyzing the rest of the information, so that they call this real-time Fourier analysis. But this is actually real-time Fourier analysis, because there's no windowing. You can have an ENL analyzing that signal. As soon as you flip it on, the ENL would be producing an analog response that's not discontinuous in time. And if there's areas where you have problems because of noise, environment, and things like that, you just don't need to have ENLs there. That's kind of not an option right now with analog to digital converters and fast Fourier transform systems that use DSPs and so on and so forth. And let me show you a graph that kind of brings this discussion to a T. A couple of years ago, I saw this presentation on MIT Review, and they were there was a paper that was published on a better Fourier transform, a better fast Fourier transform. And of course it came up in my flags during my peer review process. Now what this is claimed as a remarkable discovery. Okay, it's a remarkable discovery. This is the signal that comes out. These are the input frequencies that give this characteristic signal. This is a great graph. This could be a carrier wave, this could be one piece of information, this could be another piece of information, and this is what's transmitted over the air. In order to get the information out of this, you have to do a Fourier transform. So you have to decompose so that you pull this out, and pull this out as three different separate series. What they claim in this paper is, in this nearly optimal sparse Fourier transform was celebrated so magnificently by MIT, was that in some cases, some frequencies, some signals which are sparse enough, which means they're loose enough, you could, if you knew how loose they are, not spend time analyzing the loose areas which contain no information, and only analyze the areas which contain the information, and thus gain a speed advantage. Which means nothing at all. It's not an innovation, right? It's not an innovation in the field. It's an algorithm that scans an input signal to see whether or not there are gaps, and then ignores them. Well, like, how does that help me when the ENL just does this, and analog speeds without any training? Like, this is what frustrated me about this innovation, in that this claimed innovation, in that the ENL just does this. This is a characteristic effect of the ENL itself. The input signal that contains all of these frequencies, and then 3 output channels that contain 1, 1.1, 1.2 gigahertz signals. There's no training, there's no speed break, this is all analog. So, you know, we already beat that MIT team and the math by just doing it on the analog side. You just need 3 ENLs. So 3 ENL channels.
So one of the things that I thought of was speed test. You have to do a Fourier complicated Fourier transform speed test between the Cray and an ENL bank. That's
a good idea. Yeah. Tell you what it is right now. Well, in the models, when I generate Fourier transforms to see how you can do it on the program. So you take the signal and generate a Fourier transform. Like, it gives you the time to completion. It could be 2 seconds to time of completion, kind of thing. And then when you just run the simulation of the ENL doing its thing, it completes it in like 1/4 of a second. So even on the simulation level, you can see the time that it takes to do what the Fourier transform would have done.